So we'll start with IR spectroscopy. Here we're looking at representative IR stretches. So generally these are representative of functional groups given by bond stretches. So we know that things like the OH bond stretch shows up as a broad signal, generally above 3,300 wave numbers, so somewhere around or above 3,300. It's a very broad signal. That's indicative of an OH. Really the most representative and common other signal in the IR is the carbonyl stretch. Now these show up generally anywhere between 1650 as high as 1800 wave numbers. Generally around 1750 would be about the largest, but generally these are the frequent range for carbonyl compounds, and these are generally sharp peaks. We sometimes refer to them as swords. So we have sharp signals in this range are indicative of a carbonyl stretch. Broad signals around 32, 33, 34, 3500 are indicative of OH signals. And there's certainly many other ones. NH, we've got CH stretches if they're sp3 hybridized are just below 3000. If they're sp2 hybridized, they can be above 3000, or sp hybridized around 3300 as a sharp peak. We've certainly got triple bonds, so things like carbon-carbon triple bonds, alkynes, or nitriles. These are going to be around 2200 in that range there for wave numbers. So what we'll do in this experiment is we're going to go up to the lab to the IR spectrometer. I will show you the operating methods for collecting an IR spectra for a liquid sample and for a solid sample. And we'll use two unknowns, a liquid unknown and a solid unknown. We'll get their IR spectra, and then using comparison to literature and from a given possible set of unknowns, you'll be able to identify the identity of the unknown based upon its IR spectra. So here we are in front of a Fourier transform infrared spectrometer, otherwise known as an FTIR or just an IR spectrometer. This one comes equipped with an attenuated total reflectance or ATR attachment. It's this little plate here and some of the equipment underneath it. It allows you to place your sample simply upon a little crystal here in the middle. So there's a little hole there where we'll place the sample. That will put it in contact with a crystal that light passes through, and the interactions between the light that's passing through the crystal and your sample that sits on top of that crystal is where we get our absorptions in the IR spectrum. This is a little bit different from an absorption spectrometer that actually has to pass light through the sample to get to the detector. Now, what we are going to do with it is we're going to use FTIR to identify two unknowns, a liquid unknown and a solid unknown. And we'll show you in just a little bit the sampling for those. It's slightly different, just given the physical form of the material, but very similar. So we'll see that here in just a sec. So here's a close-up of the spectrometer itself. You can see the little hole where the crystal is and where we would place our sample. If it's a liquid, we simply have to drop a small puddle of liquid material onto that hole so that it comes in good contact with the crystal. If it's a solid, we need to place a little pile of sample on there and then use the arm that's shown right here. So it'll come across and can be tightened down to carefully pack the solid sample onto the crystal. Now, before we take a sample measurement, we first need to do a background scan on the instrument to remove absorptions from water vapor that's in the air or in the crystal, CO2, or any trace impurities that have been left on the crystal. To do this, we go up and simply click Background. The instrument will now take several background scans, average them, and then this will be subtracted from the sample measurement to remove those absorptions. So here you can see large absorptions due to water vapor. These will be removed from the sample measurement to give a nice smooth baseline. Now we are all set to take the sample measurement. So now we'll take our unknown 3, add a little puddle of this to the sampling crystal. So once we have added our sample onto the crystal, we now come to the computer and press the scan feature. Now this will initially bring you to a preview screen where it will show kind of a live sampling. It will give you an initial preview of what the spectrum will look like. And then you will have to press the scan button again to tell the computer to actually go ahead and accumulate the 8 scans to be able to get a spectrum. So here we see the initial preview scan of our spectrum. It will continue sampling live, and so occasionally you'll see small changes in the spectrum in intensity, particularly if your sample is volatile and begins to evaporate. You may need to add more onto the crystal. But now what we need to do is choose scan again to tell it to go ahead and accumulate the 8 scans and assemble our final spectrum. So here we see our scan, but it's all zoomed in. What we need to do is zoom out the spectrum, so simply right-click and choose full scale. This will show you then our full spectrum of the unknown liquid. It would be nice to have labels on our peaks to know both the intensity and the wave number. To do that, we simply choose labels, and those will be automatically placed. We can drag them around to make them more visible or clear. This looks like a pretty nice spectrum, fairly clean. We can now print it by going up to the File and then Print, and simply select the printer that we want, and then we will print that spectrum and have it for later analysis. Now we'll look at taking the IR spectrum of unknown J, which happens to be a solid, a white solid. So we'll take and scrape a small pile of the unknown over the hole, the sampling crystal. But this alone will not give us a good IR spectrum because the solid is not in firm contact with the sampling crystal underneath. So what we need is to bring this side arm around and then tighten it down. Now, how far to tighten it? We don't want to tighten it too much because then we might break the sampling crystal underneath. And there is a force gauge on the computer that will help tell us how far we need to go. But generally, we keep tightening until there is a small click, which will indicate that the force gauge, that this sampling gauge is in the right position. So we tighten it down, and then there we go. There's a small click. And now we are all set. So here we have chosen scan, and we see the preview of our solid sample. This is before I have tightened the force gauge down. So you see that without that force gauge, we have very weak signal from our solid unknown. What we really need is that force gauge to press that sample tightly into contact with the sampling crystal. So I'll do that. I'll tighten this down. Down along the bottom here, you can see the force gauge. This will tell me if I am tightening it too much. It will keep me from getting into the red zone. Oop, I've gone a little too far. There's a small click once I have reached the right spot for the force gauge. And now you can see in the sample preview, we have a much better signal to noise ratio, much stronger signal from our unknown solid. So now we can hit scan, to tell the instrument to accumulate 8 scans of this unknown solid and then compile them to give us our unknown spectrum. Here it shows us an overlay of all of the scans that we've taken. So we simply need to go over to the side here, choose the most recent sample. As before, it will be all zoomed in. We need to right-click and do full scale, and then we'll choose labels. Now here, my labels are starting to get a little bit out of whack. They're a little bit crazy, so I may need to drag them around some to be really clear about what label goes to what peak. But once I have done that, I can simply print my spectrum and then use it for later analysis. Lastly, do not forget to unscrew the force gauge, slide it to the side, and then carefully clean off the sampling crystal using Kim wipes and acetone to carefully remove all sample. Remember also to clean the bottom of the force gauge with Kim wipes and acetone.